Okay, I think we can start. So welcome again to today's central exercise session. Tiago, are you here?
Yes.
Yes, okay, wonderful. So Tiago is going to moderate the chat channel today. Once again, if you have any questions, please join us on chat, chat.um.de, and here's the channel that we're going to use for the central exercise session. Okay, so let's start right away with today's exercise sheets. But before we do that, as usual, a very quick poll. So again, I'd like to know what you found most challenging with exercise sheet number 9. Now, exercise sheet number 9 was pretty much on just one topic, and that's Kkt, Karish-Kuhn-Tucker's theorem. So I divided that into 3 different questions. What type of problem did you have most difficulties with? It either is the formulation or the adaptation of an optimization model itself. So getting from the problem formulation to the actual mathematical model. Then from that, you have to derive the Kkt conditions. So that could be a second point. And finally, you have to solve the Kkt conditions and determine the actual optimal solution. So I'd like to know which of these you found challenging, if any. It would be nice if you cast your vote here. Okay, I'll give you 5 more seconds. And then I'll end the poll now. And here's the results. So most of you found solving the Kkt conditions challenging. So we'll see if we can devote some more time to that later when we discuss our Kkt problems. Whereas formulation of the optimization model and of the Kkt conditions, was not that challenging, but obviously also not easy for most of you. Okay, we'll see examples of all of those in the central exercise problems, and I'll see if we can maybe shorten one or the other so we have more time for the actual solving process. Okay, so let's start with C96 first. So that's actually more of a high-level exercise. Because we don't actually solve the problem here. So that's a problem where we just model the problem, where we write down the Kkt conditions, where we think a little about what the Kkt conditions actually mean. We don't actually compute the solution. We will do that in 9.7 then, in the next problem. So here in 9.6, we have a triangle given by 3 vertices. The vertices are 2, 1, 4, 2, and 3, 5. So let's make a rough sketch of how that looks like. Okay, so first is 2, 1. So that's 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 1, that is roughly here. So that's the point A. Then B is at 4, 2, that is here. That's the point B. And finally, C is at 3, 5, 2, 4, 6. So that is here. So that's the point C. And that means the triangle here that we have looks like this. So the feasible set is that triangle and of course the area inside of the triangle as well. Okay, that's our feasible set here. And we want to find a point on that triangle or in that triangle that is closest to the origin. Origin is here. Closest, of course, means we take the normal Euclidean distance to the origin. Okay, so the first part of the problem is part A. Write down the Kkt conditions for that problem. So before we do that, let's first formulate the problem itself. So for Kkt, we always need a problem in the form minimize some function f, subject to inequality constraints. Those are expressed by a function g less or equal to 0, and equality constraints expressed by a function h equal to 0. The triangle here, or the area inside of the triangle, can be described by inequality constraints, obviously. So we are going to derive these first. Now, what we have here is basically lines for each of the three sides. And then each of these lines corresponds to an inequality that says all the feasible points lie to either side, either to the left or the right of that specific line here. So basically what we have to do is we have to derive equations for those lines and then find the right inequality to describe that triangle. Let's start with that connection of AB first, right? So here we have our AB. The connection between A and B is basically just the difference of B minus A. So the direction of this line here, that is 4, 2 minus 2, 1. So we get 2, 1 again. Okay. So this vector here, that is the vector 2, 1, anchored at the point A in this case. Now, if we want the equation for that line, then we actually need to find a vector that is perpendicular to that line, right? The usual equation or inequality form is in normal form. So we need to find a vector that is perpendicular, like this here. And of course, in 2 dimensions, it's easy to guess such a vector. For example, 1 minus 2 would be suitable here. And once we have that, we can come up with the correct equality or equation for that line fairly easily. What we have to do is basically this equation then looks like this. We take the vector 1 minus 2. We multiply it by x1, x2 with a scalar product. And then we say on that line, that result is the same as the scalar product of 1 minus 2 and any point on that line. Choose whichever point you want. For example, we can choose the point A here, 2, 1. Okay, so this is just the point A. We could also choose the point B. So that's an equation describing all the points on the line. Every x1, x2 that fulfills this equation is on that line here. Okay, so in other words, what we have is the equation x1 minus 2x2 equals, and this is 2 minus 2, so that is exactly 0. Okay, so that's the equation for this orange line here. This one. x1 minus 2x2 is 0. And now we want to find the right inequality. So what we want is all the points that are to this side of the line, because that's the points that we want in our triangle, right? Now, the only question that remains is, do we need less or equal or greater or equal to 0? And we can just find that out by experiment if you want. So imagine we are on that line somewhere, for example here. And then let's say we are decreasing our x1 values. We want to move in that direction, we want to decrease x1 values. Which direction of the inequality does that correspond to? If we decrease the x1 values, then this value it gets lower. So what we want here is a lower or equal, because that's what we want to have as feasible set, right? If we increase the x1 values, on the other hand, this becomes higher, and we don't want to allow that, yeah, because that's on the wrong side of our line. So if that left-hand side becomes larger, we want to disallow that, but we want to allow the left-hand side to become lower than the current value of 0 on the line. So the correct version here would be the less or equal to. Right, so that's the first equation that we get. And we can do the same thing for the other sides here. So let's see if, for example, if we have that CB here, that line, again, we are searching for a vector that is perpendicular to that. For the line itself, VBC, that is C minus B, is just minus 1, 3. So a perpendicular vector would be 3, 1, for example. And if we use that, then again, we can just write down this equation for the line in that way, vector times x1, x2, and then vector times a point on the line. For example, let's just take B. B is 4, 2. Okay. And what that means here is, well, we get exactly 3x1 plus x2 is equal to, what do we have here? 12, 14. Okay, so that's the equation for the line. And again, what we actually want is not the line itself, but all the points on that side of the line. So again, let's imagine we're here on that point of the line. We want to be able to decrease the x1 values. Right? So the right direction is, again, less or equal to. Okay, so that's our second inequality. And for the third inequality, will be this line here. All right, let's say we compute VCA. That is A minus C. That is minus 1, minus 4. So if you want a vector that is perpendicular to that one, we could choose minus 4, 1. And then we could again come up with a description for that line by just using that vector and a point on the line. For example, let's use C this time, 3, 5. Okay, so what we get here is minus 4x1 plus x2 is equal to minus 7. And again, what is the correct inequality here? Well, this time we want all the points on this side of the line here, right? So imagine we're here on the line somewhere, and we want to be able to increase x1 values this time. We want to move in that direction here. Now, if we increase x1 values, and this left-hand side here becomes smaller because we have a minus 4x1 here. So we want to allow for that side to become smaller. And that means the direction that we actually need is, again, less or equal to. Okay. So that's how we come up with the actual problem. And let's write down the final problem here. So the problem that we get want to minimize. I'll talk about the objective in a second. Let's first write down the constraints. Want to minimize an objective function such that these three constraints hold. This one here, this one here, and this one here. Okay, so the constraints are x1 minus 2x2 is less or equal to 0. 3x1 plus x2 minus 14 is less or equal to 0. And finally, minus 4x1 plus x2 plus 7 is less or equal to 0. And I reformulated those such that they read less or equal to 0, because that's the way we need them for this kind of model here. Okay, and finally, the objective. So as the objective, we are using the distance of a point from 0. So here's our origin. The distance of a point basically means the length of the vector from the origin to that point. So what we want to minimize here is the norm of our point x. And just because I don't like square roots a lot, instead I choose to minimize the squared norm of the point x. So that's x1 squared plus x2 squared. That doesn't make a difference for the minimizer, right? Because that norm is non-negative anyway. So if I just compute the square, it doesn't change a lot, because that square function, x maps to x squared, that function is monotonically increasing for positive x's, right? So whether I minimize that or the actual norm doesn't make a difference for the minimizer. It will, of course, change the actual value of the objective, but it is no difference for the minimizer itself. And once we have the minimizer, we can, of course, easily compute the value of any objective function that we actually want. Yeah. So for the minimization problem, we can take the liberty of reformulating that to have an easier objective. Okay, so that's the optimization problem. Step 1 on our way to the Kkt conditions. Is there any questions so far?
Yes. Someone asked if you could explain again how you determine that, how you find the inequalities to use. So the inequalities for the for the Kkt again.
The inequalities for the triangle, or
I guess how you determine which inequality one should use. So I guess all of them.
Okay, yeah, I'll explain one of those once again. So again, let's just have a look at that triangle once again. Basically, we have 3 lines here that determine that triangle, those 3 lines, right? And the feasible area is enclosed by those 3 lines. Let's just make, yeah, maybe I'll just use that sketch once again. Let's, for example, let's take the green line, this one here. Okay. So what I need is an equation for that green line. Once I have that, I can easily turn that into an inequality. Now, how do I get the equation? There's several ways to get there. The way that I chose is, I know there is a representation of lines in the plane in normal form. That means in the form, sorry, down here, so normal form for line in R2, that means you have a vector, the normal vector, such that you can write the line as the solution set of a single equation in 2 variables. And that single equation reads normal vector transposed x equals some value. Let's call that lambda, right? So the line basically consists of all the points x in the plane that fulfill this equation here. You just have to find the right values of n and of lambda. Now, once you have n, lambda is easy because you can just choose any point on the line, and of course that point has to fulfill the equation. So if you know a point on the line, and you just substitute that for x, and you get the right value of lambda. Well, that's what I did. That's what I did here in that step. So for the right value of lambda, I just computed my normal vector times a point on the line. In this case, I chose 4, 2. That's the point B, this one here. I know that's on the line. I could also have chosen C or any other point on the line. But those are the two that I know, right? So I'd use one of those. Okay, so to determine lambda, just choose any point on line and substitute that for x. Of course, you have to know n first, right? So that's the other problem here. N is the normal vector, and that means in this normal form, that vector is always perpendicular to the line. It's probably easiest to see this for a line that passes through 0, like let's say I would have a line like this here that passes through 0. Right? Then I would just take a vector like this, and I could say, well, this line is composed of all the points that are perpendicular to my normal vector n. This vector is n. Right? So that's just the orthogonal complement to this, the space spanned by n, in other words. Now, if you move that line out of the origin, then basically that is what this lambda accounts for. We did that in back in linear algebra in the first semester in some more details. If you want to have a look at that again, you can do that. But basically for this year, it's enough to know that you can represent a line through its normal vector, a vector like this, and a right-hand side that is suitably chosen, and you just choose it by substituting one point in the line that you know has to fulfill this equation, right? So that's the normal form. In this case, it's easy to come up with the normal vectors. That's why I chose this representation. Another possibility would, for example, would be to like determine the intersections of those lines here with the x1 and the x2 axis. And then from these points, this one and this one, you could also determine the coefficients that you want. Because again, you know, the general form for a line is something like x1, is something like x2 equals some parameter x1 plus some other parameter like this. That's probably how you got to know lines in school. So you could just take any 2 points on the line, substitute them into this system, and then solve for mu and lambda. And the easiest points that you could get is usually the intersections with the lines, if you have those, because then one coordinate is 0, and that makes it easier to solve. But of course, you could also take the points here, in this case B and C, substitute those into this equation here, and you get 2 equations, and you solve those from mu and lambda. Whichever way you choose is fine, as long as you get the right values afterwards. Okay? And then once you have that equation for the line, I'm turning that into an inequality by simply asking, well, which side is the right one? Yeah, once I have this equation that describes this green line here, for example, this one, then I know whether I want to be on this side here or on this side of the line, but just looking at the feasible set. One of these sides corresponds to a less or equal to, and one corresponds to a greater or equal to in my equation. So I have an equation of the form alpha x1 plus beta x2 equals my lambda. And then I just have to decide whether I put less or equal or greater or equal to instead of the equality. Equality is the line and less or equal to is one side, greater or equal to is the other side. And the method I usually use is I'm just varying one of the coordinates. So imagine I'm on that line here, and now I'm moving in a direction that lies in the feasible set. So if I want the green feasible set, this side here, then for example, I will be able to increase my, or decrease, sorry, I will be able to decrease my x2 coordinate without leaving the feasible set. So the question is, if I'm decreasing this value here, this x1 value, does that left-hand side decrease or increase? Whatever it does, that's what I want to allow. So if it decreases, I want a less or equal to. If it increases, I want a greater or equal to. And of course, I could also do this for x2 instead of x1, or for any mix of those two, as long as I'm moving them in the right direction. Again, if you're unsure about this, just choose a point in the feasible set, substitute that into the left-hand side, and see how the new value changes. And then if it's less or equal to the right-hand side, you know you need a less or equal to, and otherwise a greater or equal to. Any point will do. It needs to hold for all points in the feasible set. Okay, so I hope that answered that question. Any more questions?
Yes. Someone asked, how did you get with the formulation of the equations with the transposed vectors?
How did I get the formulation with the transposed vectors? So basically what I'm doing with the transposed vectors is exactly this here. So in a setting like this one, right, I want to describe that green line as the set of all points, all x in R2, where x is perpendicular to that vector n. And that's the same thing as saying, well, I want the scalar product of x and n to be 0. And that scalar product is just n transposed x, standard scalar product. So that's where this transpose comes from. So that's the scalar product. And again, we did this in the first semester. So if you feel you need to brush up on that, just have a look at the lecture notes and the exercises from the first semester. There should be some exercises on that. Tiago, more questions?
Someone asked if it shouldn't be larger or equal in the third constraint.
Larger or equal in the third constraint. Let's have a look at, so the rep one, this one. So look at that again. So equality is this line here. And again, let's say we are here at this point. Then the feasible set is to the right. Right? We want to move in that direction. So that means we want to be feasible for increasing values of x1. Now if x1 increases here, then the left-hand side decreases because we have that minus in front of the x1. So that means we want to allow left-hand sides that are less or equal to -7. We want to allow decreases here. You could also look at it in terms of x2. So if we're here, for example, then the x2 value, we want that to decrease. We want to allow a decrease here. We want to disallow an increase in x2 because that would take us out of the feasible set, right? So this is the right direction. A decrease of x2, again, have a look at this one here. That corresponds to a decrease of the left-hand side. So we want a less or equal to. I'm actually fairly certain this is correct. More questions?
There are some people writing, but
so maybe let me go on with the actual Kkt conditions then, and we'll take some more time for questions afterwards. Okay, so we have our optimization problem. Let's copy that so that we can refer to that. So there's the optimization problem. And now we want to formulate the Kkt conditions. And remember, basically the Kkt conditions use gradients or Jacobians of the objective function and also of the functions g and h for the constraints. So first thing we want to do is we want to compute the Jacobians. And of course, we formally need to state the function g and f as well. So f, that one's easy. That's the objective function. That is x1 squared plus x2 squared. So the gradient of f, that is simply, let's see, 2x1 and 2x2. The function g of x1, x2, that consists of 3 components, 1 per row. So we have x1 minus 2x2, 3x1 plus x2 minus 14, and minus 4x1 plus x2 plus 7. Okay, that's g. So the Jacobian of g would be, let's see, derivative with respect to x1. So that is a 1. For x2, we get a minus 2. Then we have 3, 1. And finally, well, that's the next one here. Finally, minus 4 and 1. Okay, so that's the Jacobian for g. And now for Kkt conditions, we introduce multipliers. We introduce a multiplier vector for g and one for h, if there is an h. In this case, there's no h, no equality constraints. And we need one real multiplier per constraint, per line of our g. So in this example, let's associate multipliers. We call those y1, y2, y3. Right, so those are going to be the multipliers. And then the Kkt condition basically states, well, we have the equations nabla, so gradient of f, x1, x2, plus the Jacobian of g at x1, x2 transposed times the multiplier vector, y1, y2, y3, plus if you had that, also jh of x1, x2 transposed times the multiplier vector. Those will be called Z usually. That has to be 0. That's the first Kkt condition. And in this case, what we get here, so here's the gradient, 2x1, 2x2. And then we have the Jacobian. We transpose that. So we get 1, 3, minus 4, and minus 2, 1, 1, times our multipliers, y1, y2, y3. There's no h, so that term is just 0. And that is 0, and that 0 specifically means the 0 vector. So we get 2 rows here. So vector 0, 0. Okay, so what we get here is the 2 equations, 2x1 plus y1 plus 3y2 minus 4y3 is 0. And then 2x2 minus 2y1 plus y2 plus y3 is 0. Okay, that's the first part of the Kkt conditions. Then, second part, we need feasibility. So that basically means we need to make sure that g of x is less or equal to 0. So in other words, the conditions that we wrote down in the optimization problem already, oops, and those were x1 minus 2x2 is 0, then 3x1 plus x2 minus 14 is less or equal to 0. Oh, sorry, that's less or equal to here as well. And minus 4x1 plus x2 plus 7 is less or equal to 0. Right, so that's feasibility. Then we have conditions on the multipliers. Those are very easy. We want the multipliers to be non-negative. So y1, y2, y3 are all non-negative. And that's only true for the multipliers associated to inequality constraints. Multipliers for equality constraints may have an arbitrary sign. And finally, again, for those multipliers associated to inequality constraints, we have complementarity conditions. So let's write those down as well. Oops. And what that means is each multiplier is associated to one inequality, and the complementarity condition states either the multiplier is 0 or the corresponding inequality is strict, so fulfilled at equality. Of course, both is also fine, but one of those things at least must happen. And the way we state this is usually the product of a multiplier and the part of G that corresponds to it, like here, this one, that has to be 0. And the same is true for y2 and its corresponding constraint, that is 3x1 plus x2 minus 14. And finally y3 and its corresponding constraint minus 4x1 plus x2 plus 7. So it's a 7 here, not a lambda. Okay, so this is the Kkt conditions for that problem here. That's also part of it. And that means to find a solution, what we have to do is we have to solve this system of equations, linear and nonlinear equations, to find values for the x's and for the y's where this is all fulfilled. And if you find such a point, that's called a Kkt point. And then this is a candidate point for an optimum. Okay, so that concludes part A. Questions up to this point?
Someone asked where in the equation is plus Jacobi, so I'm not sure what it means.
Me neither, actually. So here is the plus Jacobi part. I guess that's what you're referring to, but I don't really get the question.
Okay, and someone also asked if you could briefly sketch how this concept would translate to R3 if the feasible set is not some nice figure like a cuboid.
If the feasible, so if we have a feasible set in R3 that doesn't look that nice.
Yeah.
Actually, it's pretty much the same concept. Dimension doesn't really matter here.
Just a second, the guy who asked about the plus Jacobi said second line. So maybe
second line. So this one here. What was the question again?
Where in the equation is plus Jacobi?
Maybe he's missing this part here. So if that's the problem, if you're missing this part with a JH here, in this specific problem, we don't have an H. So that is just 0. Right? So the function H, that contains all the equality constraints. In this problem, we don't have equality constraints. We'll see an example that has equality constraints in 9.7 in the next central exercise problem.
Okay,
so hopefully that,
yes, so I think
that answers the question. Okay, good. So what was the other one again? I forgot. Oh, R3, about R3.
Yeah.
So that doesn't really make a difference if you're in R3 or R2, just becomes larger, of course. I mean, here we have a problem that uses two variables, it's easy to imagine one that uses 3 variables. It just adds something to the objective, just add something to the constraints. And of course, what makes this problem feasible or treatable is that we have constraints that are linear. So those lead to more or less easily solvable equations in the Kkt formulation. If those were nonlinear, to describe more complicated sets, then the equations that we get would become more complicated. And probably at a certain point, we would not be able to solve those anymore, at least not by hand. Yeah, but the concept itself is totally the same. You take these equations again, you associate one multiplier per inequality. And of course, there may be more inequalities if the set becomes more complicated, but same concept again. And then you just state this condition here, and you add feasibility, non-negativity, and complementarity constraints. So this whole thing, of course, blows up a little if the dimension and the number of constraints becomes larger, but the concept is totally the same.
Yeah, thank you.
Hopefully that answers the question.
Yeah, and there's one more question. I'm not sure if you're familiar with the term slack variable.
Mm-hmm.
They ask if this multipliers is the same as a slack variable from management science.
It's not. So the multipliers are a generalization of the dual variables from management science. Actually, if you apply this to linear programming, then the multipliers exactly correspond to the dual variables from LP duality. And if the problem is not linear, then this Kkt multipliers, those are an extension or a generalization of that concept of duality. So those are more or less dual variables. Any other questions?
No. Someone said there is missing a equal 0 in the multiplier part of y3.
Oh yeah, thanks a lot. I'll add that here. Okay, part B. Part B asks for the number of multipliers that we need here. We've answered that already. And the answer is we need 3 multipliers. In general, it's also easy to answer. We need 1 multiplier per constraint. Regardless of whether this is an inequality or an equality constraint, it's always 1 multiplier per constraint. For the inequality constraints, that multiplier is restricted to non-negative numbers. For the equality constraints, the multiplier can also take negative values, but is always 1 multiplier per constraint. Okay, and finally part C, the question here is, what would it mean if all the multipliers were non-zero? What about 1 or 2? So let's have a look at those cases. All multipliers non-zero. Well, what would that mean? If we look here at the Kkt conditions, all the y's, y1, y2, y3 are non-zero. That means here, for these complementarity conditions, we would then need to make sure that these parts here become 0. And that means all the constraints have to be fulfilled at strict equality. Right? So that first case, all multipliers non-zero, that means all constraints have to be satisfied at equality. And what does that mean for our triangle setting? We have a look at this sketch here. All constraints satisfied at equality means we need a point that lies on this line and on this line and on this line. And as you can see in this specific triangle, there is no such point. And actually that's true for every triangle apart from one where all lines meet in one point. So if the triangle is only 1 point, then this would work. Otherwise, that's just not possible. So if all the multipliers are non-zero, then something infeasible is happening here. Okay, so that's a thing that just can't happen. Right, that is not possible in this problem. Now let's look at the other cases. What about two non-zero multipliers? Now what that would mean is we have two constraints active at the same time. So we are at the same time on two of these lines. So either on these two, oops, sorry, this one and this one, which would mean this is the x values that correspond to that, or maybe on these two, and then we get this point as a solution, or maybe these two here, and then we get this point as a solution. So what that means is we are on one of the vertices of that triangle. Right? Two active constraints at the same time means we're on one of the vertices. Two constraints are active, and that means the solution corresponding to that is a vertex of our triangle. What about one non-zero multiplier? Now if that's the case, one constraint is active, so we are on one of these three lines, and that means the solution could be a vertex, but it doesn't have to. It could also be somewhere on the sides, right? One constraint is active. That means what we have here is solution is on the boundary, on a boundary. Specifically, the one boundary line that corresponds to the non-zero multiplier. And finally, let's also discuss that last point. What about no non-zero multipliers? So all multipliers are zero. Now that would mean the solution doesn't have to be on the sides. It could still be there, but it could also be somewhere in the interior. Okay? No constraints have to be active. That means the solution could be in the interior as well. And for this optimization problem, that would happen if we shift the triangle such that it contains the origin. And of course, that origin is the point that has the least possible distance to itself and is in the triangle. Yeah? That would be a situation where we get that. For this specific problem setting here, with the triangle that doesn't contain the origin, like this one, that cannot happen. Okay. Again, questions before we start with 9.7? I guess we're going over time today.
Yeah, no questions.
No questions so far. Okay, good. Okay, so we learned about formula. Yeah, sorry.
Someone asked how much time should it take for us to solve such a problem in the exam?
How much time should it take for you to solve such a problem? Well, hard to say specifically. It always depends on the numbers, of course, and it depends on the questions that I'm asking. Let's say usually for the exam, I wouldn't use a large problem, like for example, 9.7, that took quite some time, or some of the problems in the homework also take quite some time, but there are easier ones. Let's see, didn't I put an exam question in there actually? Yeah, for example, consider 9.5, H9.5. So that is a problem that was on an exam. And I think the idea was to spend around 10 minutes or so for solving that. So that shouldn't take you too long. Yeah, of course, that doesn't ask for very tedious computations here. But it could also make a problem that just has nice numbers, where you could do the computations, but they all turn out nice and easy, so you don't have to spend that much time. Of course, I wouldn't have to be able to do something like 9.7 on the exam. That's just too long, but maybe parts of that.
Okay, someone asked if you could scroll down a bit.
I could scroll down a bit, of course. How far? To the end, I guess. So
Yeah.
that's the last current question. I just start with 9.7.
There is one more ask. Could you explain again how we got the optimization function?
How we got the optimization function? Yeah, that one's easy, hopefully, so I can try. So what we want is, we have this feasible set in here somewhere. Let's say that looks somewhat like this. Yeah, so that's our triangle. And what we want to minimize is the distance of a point in the triangle to the origin. So here's the origin. So how do we measure the quality of a solution? So let's say this is the optimal solution. What quality would it have? Well, we would just measure the distance between these 2 points, right? So let's say this is the point X, this is the point 0. Then their distance is exactly the norm of their difference, right? So as one point is 0, it's just the norm of X. And now what I did, that norm of X, that would be the square root of x1 squared plus x2 squared, like this. What I did is I made things a little easier, because my argument was this is non-negative anyway. So if I just apply a square to that, I won't lose anything. I won't lose negative solutions, right? So that doesn't really matter anything. Plus the square function itself is a continuous and monotonically increasing function, right? That's the function t maps to t squared. That is continuous and monotonically increasing on the non-negative numbers. And I just established that I'm just interested in non-negative numbers. Okay, so whether I optimize this function here or this function here, the square of that, that doesn't really make a difference for the right result. So for the X values of the result, right? Because of monotonicity, if that is minimal, then that is minimal as well. You could also argue that what I'm doing here is I'm minimizing the argument of the square root. And as the square root looks somewhat like this, right? So that's the square root function. As the square root is also monotonically increasing, that of course means if I can minimize the argument, then I also have the best possible value for that function. So I'm just minimizing the argument of the function because that's easier. Okay, I hope that answers this question. Anything else, Thiago?
Yes, but I guess we should move on. Or
Yeah, maybe we move on, and maybe we can take a minute in the end for those who still want to stay with us.
Yeah.
Okay, so let's move on. Maybe I can shorten this 9.7 a little and concentrate on the parts that we haven't discussed so far. That's specifically the solution of Kkt systems. So here we have an optimization problem that we need to solve. That's minimize x1 squared plus x2 squared. Sorry. Subject 2. So what we have is x1 squared plus x2 squared is less or equal to 5. I will reformulate that right away and write minus 5 is less or equal to 0. Then I'll add the other inequality constraints. We have x1 is greater or equal to 0, or I could write this as minus x1 is less or equal to 0. And I'll do the same with the x2 constraint. And then we have one equality constraint here as well. That is x1 plus 2x2 equals 4. Or let me reformulate that as well. Minus 4 equals 0. Okay, so we have that in the right form already. This here is the function f, our objective. These inequality constraints here, those make up for the function g, g1. So g is x1 squared minus x2 squared minus 5 minus x1 and minus x2, like this. And this function here, that is h. So h is x1 plus 2x2 minus 4. So here we have an equality constraint as well. And as usual, we compute the Jacobian matrices of these functions to obtain the Kkt conditions. So gradient of f, we did that one already, 2x1, 2x2. Then the Jacobian of g. So that is 2x1 just a second. I think yes, I actually mixed up a sign here. So that should be a plus, of course. So 2x1, 2x2. And then we have a minus 1, x1, a 0 for the x2s, and in the last row, 0 and minus 1. So that's the Jacobian of g. And finally, the Jacobian of h. That would be 1 and 2. Okay, so we're using multipliers. Again, for g, I'll use multipliers y1, y2, y3. And for h, I'll use a multiplier that I call set1. And with that, we can write down the Kkt conditions. So remember, Kkt conditions, the gradient of f plus the Jacobian of g transpose times the multiplier vector plus the Jacobian of h transposed times the multiplier vector is 0. So in this case, that translates into the following equations. So this gradient is 2x1, 2x2. Then we get the transposed Jacobian times the multipliers. So for the first row, that is 2x1, y1 minus y2 plus 0 times y3. For the second row, it's 2x2, y1 plus 0, y2 minus y3. And then we have that h part here, that h is 1, 2. So we get, again, we have to transpose that. So we get a 1, set 1 on the first row, and a 2, set 1 on the second row. And the right-hand side is always 0. Okay, so that's the first two Kkt conditions. Then we have to add feasibility. So that means we have to add the inequalities once again. x1 squared plus x2 squared is less or equal to 5. x1 plus 2x2 equals 4, and x1, x2 is greater or equal to 0. Then we need non-negativity of the multipliers. So y1, y2, y3 is greater or equal to 0. And remember, set 1 is associated with an equation, with an equality. So no constraint on that multiplier. And finally, we get the complementary slackness constraints. So that is y1 times the associated equation, inequality, that is x1 squared plus x2 squared minus 5 is 0. y2 times minus x1 is 0. And finally, y3 times minus x2 is 0. Okay, so this here, this is our Kkt system. And that's the one we have to solve. Questions so far, before we actually do the solving of that?
No.
No questions. Okay, great. So before we dive deeper and try to find the solutions for that, let's first try and exclude a few easy cases. And the one that we can easily exclude is the case y2 and y3. If those are simultaneously non-zero, then that immediately implies that x1 and x2 have to be 0. And on the other hand, that conflicts with this equality here. Okay, so 0 plus 2 times 0 is not 4. So that case cannot happen. Okay, so let's exclude that right away. First possible case, y2 is not 0 and y3 is not 0. That would imply x1 and x2 are 0. And that would imply, that conflicts with x1 plus 2x2 equals 4. Okay, so that case cannot happen. And that means we can structure by those two variables, x2 and x3. At least one of those has to be 0. So let's start with the case where y2 is 0 and y3 is also 0. Let's try to see what happens then. So if those are 0, then that means the axis may take on whatever value they want, as long as it's non-negative, of course. And some of the equations become a lot easier. So let's copy that here. Yeah. Oh, yeah, still pointing. So remember, that was our Kkt system. Now, if y2 and y3 are 0, then that means this here vanishes, this here vanishes, right? So the first equations become easier. We still have to take care for that y1. And while we add it, let's also assume y1 is 0. We'll treat the other case in just a second. If y1 is also 0, then this here vanishes as well. So it makes things a lot easier. So what we have now is these two equations here. And we also have the other equations down there. We can try and solve these. Okay, so specifically we have these two equations, this equation, that's 3 linear equations for the variables x1, x2, and z1, and we can just try and solve this. Okay, so from these two, solve for x1, x2, z1. And once we have solved this, we just check whether the solution is actually feasible. If we do this, I'm going to demonstrate this. It's just Gaussian elimination. What we get is x1 is 4/5. x2 is 8/5. And sorry, set 1 is minus 8/5. And then we take the solution, and important point, we check feasibility. So we know that it's feasible for the orange equations because that's the one we solved. So we have to check whether it's feasible for this green inequality. And just do that by substituting the values, computing the left-hand side, and then comparing that to 5, and we'll see it works. And of course, we have to take this into account as well. And obviously, that's satisfied too, okay? This one is also part of feasibility, of course, but we all set these y's to 0, so we don't have a problem here. So in this case, the solution is actually feasible. And that means we have a Kkt point. So that's our first candidate for an optimum. Okay. And now we just have to work through the remaining cases. I'll give you at least one. Let's see. So remaining case here, we can have a look at the case y2 equals 0, y3 equals 0, but y1 does not. So that's the opposite of what we just did, basically. Let's again pass the system here. Again, if y2 and y3 are 0, then that means these two terms will vanish. If y1 is not 0, then that will imply that this here is fulfilled at equality. So here we get another equation. This needs to be fulfilled at equality now. And again, we get a set of equalities, or we can hopefully solve. We have this here. We have this here. And in addition, we now have this equation. So we get 4 equations, and we solve that for x1, x2, set 1, and y1. And again, it's possible to do that. So using these 4 equations, we solve that for x1, x2, z1, and y1. It's not that straightforward anymore because we have a nonlinear equation in there. But we could just use the linear equations to eliminate everything but one variable, then substitute that into the nonlinear part and get solutions for that remaining variable, and then just back substitute that. Okay. So if we do that, we get 2 possible solutions for the x's. So one possibility, let's call that x star. One possibility would be minus 2/5 and 11/5. And obviously this one violates feasibility here, right? Because that is not greater or equal to 0. So that's not a feasible solution. We can exclude that right away. And the second solution that we get is 2,1. Okay, so what about 2,1? That's at least positive. So that is that condition here is satisfied. Just a second. But if we have a look at the y1 that we get here from that solution, then we'll see that is -1. Okay, and that is not greater or equal to 0. So Feasibility is again not satisfied. So it's important to not only check the X values for feasibility, but also the multipliers that you get. In this case, it's the multiplier that doesn't play by the rules, right? So this is infeasible with respect to Kkt conditions. So again, not a feasible Kkt point. And then of course you could play through the other two cases that are remaining as well. Let's give you a quick summary of that. So one possible case is y2 is 0 and y3 is not. y3 not being 0 immediately implies that x2 has to be 0. Right? Remember the Kkt system? Looks like this. If y3 is not 0, then x2 has to be 0. And again, we can just eliminate things here. So y2 is 0. X2 is 0. So this here vanishes. This here vanishes. This here vanishes. This vanishes as well. So that we get x1 equals 4. Yeah, not a good choice of coloring. So we immediately get the solution x1 equals 4. And where we can then just try and put that in here. And obviously 4 squared is 16. That's not less or equal to 5. Okay, so again, the solution that we infer from that case is no Kkt point. And finally, last case. That would be the case where y2 is not 0, but y3 is. Then again, have a look at that system. y2 not being 0 immediately implies that x1 has to be 0 because of this constraint here. Okay, so what happens here is, let's see, y2 is 0, so that vanishes. Sorry, y2 is not 0, my bad. y3 is 0, that vanishes here. And x1 is 0, so this here vanishes, and this here vanishes as well. This here vanishes, and this. So what we get, again, immediately is a value for x2. x2 is 4 over 2. So this time, if we put that in here, x2 squared, that's 2 squared, that's 4. That is less or equal to 5, okay? So that will work. But what about the multipliers? We have to figure those out as well. And you can either do that by trying to compute the values for the multipliers, or again, by a little case distinction. So we know y2 and y3 already. Let's just check y1. Subcase of that. What about y1 being 0? Well, if y1 is 0, then we can immediately solve for z and for y2. So we know the values for x1, for x2, and from that and the equations that we have left, we get z1 is -2. And we also get y2 is equal to z1. So that would also be -2. And that is again a contradiction. The y's need to be non-negative. And finally, subcase y1 is not 0. And well, if y1 is not 0, then that's the easier subcase even. By this condition here, we know that this here has to be, this here has to be fulfilled at equality. This has already been simplified. It's this condition here. So that means x2 squared has to be equal to 5. And we already know x2 squared is 4, so it's not equal to 5. So again, a contradiction. Okay, so basically we go through all the possible cases here. We make use of the complementarity conditions here to get additional equations. And then we try and solve these equations. And in some of the cases, we will get feasible points, Kkt points. In some cases, we will not get feasible Kkt points. It's important to check all the feasibility constraints. So not just those for the x's, but also those for involving the y's, right? Don't forget about those, please. Finally, in summary, to conclude that problem here, what we get is one unique Kkt point, and that was the point 4/5 and 8/5 from the very first case. That is the only Kkt point. Okay, so we just have one candidate for a global minimum here. And we know that the function that we want to minimize is continuous. We know the feasible set is described by inequalities and equalities, so that's a compact set. And that means f assumes that minimum on a feasible set. So this x here must actually be a minimizer. Okay, so f is continuous. The feasible set is compact. And that means f assumes a minimum over the feasible set. So as x is the only candidate, x must be a minimizer. Okay, and thus we have solved this problem. So again, it's just amounts to going through all the possible cases. Usually you distinguish these cases by looking at the multipliers associated to inequality constraints, because when those are not zero, that immediately gives you new equalities and you want to use those. And then you solve those. Try to check if the results are feasible with respect to all the Kkt conditions. And if they are, you have a candidate point, a Kkt point. That's candidates for minima. And if you have more than one, then in the end, you just check which one of these is the actual minimum, if there is one. Okay, that concludes 9.7. Questions?
Yes, someone asked if they had this in the exam, could they stop in the case 2 and say that because of convexity, they found one solution and that's enough?
Good catch. Yes. So very clever thing. Yeah, I wanted to mention that as well. Actually, our set f, or our function f is convex. And also the feasible set is convex. Yeah, that's because g and h are convex functions. And that means, as you know, every Kkt point is a minimizer. So once we have found one Kkt point, we know that is a minimizer. So we can actually stop there. Okay? So every Kkt point is a minimizer. And that means we can stop after we have found the first one. If we're actually only interested in one possible minimizer. If you want to find all minimizers, of course, then we have to go through all the cases again, yeah, because there might be more than one. Okay, but thanks. Very clever question, actually.
There is also one more question. Is there an easy way to know how many cases need to be computed given a number of y multipliers?
Is an easy way to know how many cases have to be. Well, basically what you have to do is you have to go through all possible combinations of the y's being 0 or non-zero. So it's something like 2 to the number of multipliers in the worst case. Obviously, you'll want to exclude cases beforehand if you can, right? So if there's combinations of multipliers where you can immediately see that cannot be feasible, then you can treat those very briefly beforehand. And maybe there's combinations like things like that tell you like that one multiplier can never be 0 or that one multiplier has to be 0 all the time. Then of course you will have to you will want to exclude these beforehand. But in the worst case, it's 2 to the number of multipliers cases. If you want to go through that based on multipliers, that is, yeah, you could also try and make case distinctions on a different basis, and sometimes that might be more clever. More questions?
Yes, there was this question from before. How could be integers constraint included? How would we deal with non-continuous variables?
Yeah, in continuity. So integers is a whole other story. So if you want to include integers here, then of course Kkt per se doesn't work anymore, because that only works for functions that are differentiable. And if you just work on the integers, just on discrete points, then that whole differentiability thing completely breaks down. You need open sets to define differentiability at a point. Yeah, so you need a neighborhood of a point. So one possible approach to this integer optimization is to use Kkt as a relaxation. So what you could do is you could forget about the integers, try to find an optimum using Kkt of the continuous problem with no integer constraints. And then if you're lucky, that might already be an integral point. In that case, great, you're done. If it's not, then you could try and find an additional equation or an additional inequality that excludes the point that you have currently found, but that does not exclude any of the integer points. And then you just repeat the process. So that's one possibility. That's something that you probably know already from integer linear programming. That's known as generating cuts. So those additional inequalities that would be called cuts. And for example, one famous class of cuts is the Gomery cuts. You may have heard of those already. Those work for integer linear programming problems, and there are techniques like that for nonlinear integer programming problems as well. But usually things become really hard really fast if you're dealing with integers and nonlinearity. Yeah, integers is bad enough. You don't really want to have nonlinearity on top of that. Another possibility would be to express the integrality constraint as a nonlinear equation. So, for example, if you had a binary constraint, that's the easiest one. If you had a constraint that says something like x1 is either 0 or 1, something that you encounter very often in practical problems, then you could express that as a nonlinear constraint by simply adding the constraint x1 times 1 minus x1 is 0. Because that is only fulfilled if x1 is either 0 or 1. Okay, so you forget about this here and you just replace it by this condition. And then you have a nonlinear problem, but without integrality constraints. And of course, you can do this on a more general term. If you have, for example, a variable that can become 0, 1, or 2, then you can use something like x2 times 1 minus x2 times 2 minus x2 is 0. As long as you have an upper bound, that will work. On the other hand, the equations that you get here tend to become pretty bad computationally. And the main cause for that is what you have here is something like minus x1 squared plus x1 is 0. So the graph of that function looks something like that. And that's not a convex function anymore. So problem is, with this technique, you usually get an optimization problem that is not convex. So Kkt still works, as we have seen, but it becomes pretty tedious to go through all the cases, do all the computations, whereas the convex cases work reasonably well. The non-convex cases tend to become very, very hard computationally. Yeah, so that's something that you could do, but you usually don't. Okay, does that help? Does that answer the question in a somewhat vague way?
I don't know.
If you want to know more about this, I'll be happy to discuss that, because that's one of my research topics, actually.
Yes, thank you, he said. There is one more question. Someone asked, when is a set convex?
When is a set convex? There's a nice video on that, but as a very short explanation, a set is convex if and only if for every 2 points in the set, the line connecting those is also completely contained in the set. So you have a set, you choose any 2 points, and then the line connecting those two must be completely contained in the set, no matter which points you choose. So here's an example of a set that is not convex. Yeah, for example, if you choose these 2 points, then you're good. Lines in there. If you choose this point and that point here, then the line connecting those is not completely contained in the set, right? So it's this part of the line here that's outside of the set. So this is not convex. Okay. More questions?
There is one that I skipped, but I'm not sure what. So he asked, could you explain the last 2 rows, but I don't know from where.
Oh yeah. So if that is still the current question, maybe you could give us a page number or something like that.
Someone asked if there is any infos on the exam.
There's info. So I just received information on the exam today. Actually, I received a confirmation that from your department, from your examination board, that I can actually proceed with my plans. So let me work those out in more detail, and then I'll present specific information on the exam next week. So next Monday, probably after the central exercise session, I'm going to give you more details on the exam. You can already register for the exam if you want to. So that registration on Online for the first exam date open today. That first date should be on the 13th of August, I think. And registration is open until 6th of July or so. So you can also wait until next week to get the specifics about the exam before you decide whether you want to register or not. Okay, but there'll be more details next week. And before that question comes up, I hope I also have a specific date for the retake of Math 1 next week.
Yeah, someone asked if we have multiple dates.
Sorry, what about multiple dates?
Someone asked if there is multiple dates for the exams, I guess.
Yes, there's, as usual, there's one first date that is going to be the 13th of August, if I recall correctly. It's on Online. The second is sometime by the end of September. I think it was the 29th, but I'm not sure about that. So as usual, there's going to be one first examination date and one retake.
Yeah, I guess that's it.
Okay, great. So thanks, Thiago, for moderating. Thanks for attending and for your questions. And I hope I'll see you on Thursday in the tutorials then. Goodbye.
Bye.
Bye, Thiago.